Okay, welcome everyone again to another Math 6A discussion section. Um, for this one, this last week before finals week, I'll be talking about surface integrals and the somewhat related topic of the fundamental theorems, Green's and Gauss's theorem, that sort of allow us to think about surfaces in relation to either the volumes they bound or if it's in the plane, the boundary curve. To begin with, we want to just first talk about what surface integration is. So here we can have two possibilities. We can either be integrating a scalar function or a vector field. The scalar function is slightly simpler. So what we do is we take a domain D that's a subset of just the plane, giving us parameters for the surface. And then we say that our integral over the surface can be found by integrating over the domain, evaluating the function at the point that it's parametrizing, and then multiplying by this sort of area element that's going to be the normal vector magnitude. And so we can, sometimes we know what that is if it's a very familiar surface like a cylinder or a sphere. Often if it's given with just an explicit parameterization, the best way to deal with it is to just take the cross product of the two partial derivatives at a particular point. And then this last integral is the integral of a region in the plane, is something we know how to do. So what does this look like? Turn on notation. We've got problems like this that we might want to deal with, where we've got our known function, and we know our surface with this parameterization, and here we're thinking over the unit circle. And so our first goal is to figure out what this normal vector is and what the function evaluated in our surface is. And so for the normal vector, we're interested in the partials of our parameterization. And so if we take the u partial, we get 1, 0 minus 2u, and the v partial is going to be the same kind of thing, 0, 1 minus 2v. And so if we want to take their cross product to get the normal direction, we can see that our x component is going to be 2u, our y component is going to be 2v, and our z component is going to be 1 by using the cross product formula. And so that tells us that the magnitude of n is going to be the square root of 1 plus 4u squared plus 4v squared, which is not the friendliest looking thing, but it'll work out okay. And then we also need to know what our function is. So if we take f and evaluate it at r of uv, we're looking at 5 minus the quantity 1 minus u squared minus v squared. Oh goodness, there's a typo here. I meant to be asking about 5 minus 4z. For which this problem is much simpler. And And so if we have that, if we do 5 minus 4z, and I'll correct this in the one posted, we see that our function value here is going to be 1 plus 4u squared plus 4v squared, which is, exactly the magnitude of n squared, which is going to be a helpful simplification here. And so the surface integral that we care about of f against this surface area element ds is going to be given by the integral, and here I will just call it d over the unit ball in R2, of 1 plus 4u squared plus 4v squared to the 3 halves, because we've multiplied the first against that to the 1 half, and I'll call it du dv. But here, since we now just have an integral in the unit circle that we're interested in, we can think about what coordinate system is going to be best to carry out this integral, and since we're depending on u squared and v squared in equal quantities, we can see that it's actually going to be more pleasant to do this integral in polar coordinates than in the way it's written suggests that this is Cartesian coordinates u and v. And so we could actually say that this is going to be the integral, which would be 0 to 1 and 0 to 2 pi in the unit, in describing the unit ball, of 1 plus 4 r squared, and here this notation is not the greatest because we had called, well, it's an r. We'd called r our parametrization function, and here I'm using it for the radius in polar coordinates. It'll be okay. And then we need our area element here, which is r d theta dr. The integral of theta is easy, as we don't have any dependence on theta, so we're just going to pick up a factor of 2 pi. For the integral in r, we can think about, let's do this in blue, making a substitution here where we will call w 1 plus 4r squared, because the factor of r from the area element is exactly what we need to do a quadratic change of variables here. And so if we do this, sort of third change of variables in this problem so far, we're going to get, let's see, yeah, there's the 2 pi from the theta integral. We're going to get a factor of 1/8 from the change of variables, and then we're going to get, since this is w to the 3 halves, the W antiderivative is 2/5 W to the 5/2. And if we look at our bounds of integration, if r is going from 0 to 1, then w is going to go from 0 to, sorry, not 0, from 1 to 5. Which means that our final value for this integral is going to be sort of not incredibly pleasant looking pi over 10 times 5 to the 5/2 minus 1. And for the second problem, I wanted to talk about integration over a sort of a known, somewhat friendly surface, where we don't know explicitly the parameterization, but that's nominally something that we could choose, and we might think about what's the best way to choose a parameterization. Since we're talking about a unit sphere, there's almost always the correct way is going to be in terms of the angles theta and phi from spherical coordinates. And so, in fact, we even, a thing that we could remember or rederive, but is sort of good to know, is the normal vector in terms of theta and phi is minus a factor of the radius squared, but here the radius is 1, sine phi times our point in the parameterization, r of theta phi. And so since we have this, can look it up or whatnot, we can see that the sort of area element that we need, the magnitude of n, is going to be just sine phi, and really it should be absolute value sine phi, but since we know we're in the region where phi is ranging from 0 to pi, the sign is always non-negative, and so the absolute value is equal to the value. Then if we were to look at f of r of theta phi, we can see that the exponential terms, e to the x squared, e to the y squared, and e to the z squared, that's going to wind up being just e to the r squared. We're on the unit sphere, so r is 1, and so that just gives us a factor of e. And then the value of z that we wanted is r cosine phi, and so 1 cosine phi. So our function that looks complicated in Cartesian coordinates is quite simple when evaluated on the sphere. It's just this multiple of cosine. And so the integral that we're after, surface of f ds, so we need to take phi from 0 to pi, theta from 0 to 2 pi, then an e, cosine phi, sine phi, d theta d phi, And then we don't have a dependence on theta, so the theta integral is just going to give us a factor of 2 pi. Our integrand here, we've got the cosine phi sine phi. We're going to want to use the identity that is 1/2 of sine of 2 phi. And so I'll write this as pi, pull out the e, I'm going to put the integral from 0 to pi, sine of 2 phi d phi. And then if we take the antiderivative of sine, we'll get 1/2 cosine of 2 phi, evaluated at 0 and pi, and so we'll be taking the difference of cosine evaluated at 2 pi and cosine evaluated at 0, but those are both 1, and so actually this that integral vanishes, and the full value of the function integrated over this thing is 0. And this one we can check to see if that makes sense, and we can see that our function on the sphere is only dependent on the height, z, because the exponential terms are all constant on the, on a fixed sphere. And we've got as much of the sphere above the axis of positive z as there is below it. And so we can sort of expect a cancellation between the sort of positive upper hemisphere and the negative lower hemisphere. And so it's reasonable that it should cancel out like that. Alright. The other kind of surface integral that we're sometimes interested in is the integral of a vector field dotted with the sort of vector version of the surface element ds. And so here I've put in the notation, I sometimes drop the vector hats, but I am highlighting it on this one. And here it's going to be very similar, that we want to just evaluate our function. So here our vector field along the parameterization, and incorporate the normal direction. And here we're going to do that by just taking the dot product of our vector field in terms of u and v with that normal vector itself. And so its scaling factor is going to account for the norm, but we also need the direction. And then if you write out the normal vector as the product of its magnitude and the unit vector giving its direction, little n, you could see that this is exactly related to the notion of a scalar integral of a vector field by taking, the scalar integral of the surface integral of a scalar function, too many things starting with s, by the fact that the scalar function that we want to integrate is just the dot product accounting for the direction of f with the unit vector, and then the magnitude is accounted for in the scalar surface element ds without a hat. Alright, so problem that I want to go through here, we've got a vector field. We're computing the flux of a vector field through a surface is is that quantity, is the integral of it against the surface element. And so here we've got a surface that is, you know, a little patch of a plane. It depends linearly on its variables. And it's going to be this little, like, triangular patch that if we draw out what's going on in UV, this line, U plus 2V equals 3 is going to give us this little triangular patch that we're interested in. So, as before, we need to compute what our normal vector is. And so here, if we think about the U partial, we're going to get a 1, minus 1, 0, and the V partial is going to give us 0, minus 2, 1. And so if we take the cross product of those two, what we wind up with is this vector minus 1, minus 1, minus 2, which is pointing downwards. It's something of an unusual choice, but like if we're given this parameterization, the parameterization is like determining an orientation, so we'll go with it. Because, but like it's sometimes a thing to check if you're being asked for like the upward facing orientation, then you would have to like multiply the parameterization by a factor of -1. But okay, that's our normal vector, and it's a constant normal vector, which is quite pleasant. That's also telling us that it's a plane. Then we could think about what is the value of this function, f(r) of uv. And so the y component in the parameterization is 3 minus u minus 2v. The x component is u. And the z component is v, so minus z squared is just minus v squared. And so then our integrand is just going to be the dot product of those last two vectors. That's f dot, thing that we want. If we think about parameterizing this region, we can see that v goes up to 3/2, and that this line is something that we could solve as u is 3 minus 2v, giving this sort of right bound in u. And so if we parameterize v on the outside, that's a 3/2. You can clear that up a little bit. It's 312. So v on the outside, u goes to 3 minus 2v. And inside we've got to take the dot product of these things. And so we can see that we're going to get a constant term of -3. We're going to get a positive u from the x component and a negative u from the y component. So there won't be any u terms. We are going to get -2v, plus 2v from the x terms, and we're going to get a plus 2v squared from the y terms. and that, or sorry, from the z terms, and that accounts for everything. And so that was the integral du dv, and let me draw in that sort of boundary to make it clearer. And now we've got just a double integral iterated as usual. Since we don't depend on u, this u integral is just giving us a factor of 3 minus 2v, multiplying our integrand, so we get 0 to 3 halves. Multiplying out 3 minus 2v, well, okay, we get 3 minus 2v times minus 3 plus 2v plus v squared. If we multiply that out, we're going to get a minus 9. The v terms are going to be coming from 6v from those, and a 6v from those two. So that'll give us 12 v's. V squared, we're going to get 3v squared from there, minus, oh, sorry, this is plus 2v squared, so that's going to be 6v squared, and then minus 2v squared, or minus 4v squared from those. So plus 6 and minus 4, which gives us a total of 2v squared terms in the end. And then the last, for v cubed, we're going to get a minus 4v cubed. This gives us a polynomial in v, so we can take its antiderivative. A minus 9v, we're going to get a plus 6v squared, we're going to get a plus 2/3 v cubed, and a minus v to the 4th, 0 to 3 halves. And then evaluating these, we get minus 27 halves, plus 27 halves, plus 9/4, minus 81/16, and the first two terms cancel. 9/4 is 35/16 multiplying by 4. 35 minus 81 is going to give us minus 45 over 16 as our final answer. All right. So, let me put that on the screen. The last sort of main topic in the course here are these two fundamental theorems that both have this sort of flavor of we're relating the integral of some derivative quantity some kind of derivative over the bulk of a region, and finding that that's equivalent to doing a corresponding integral of the vector quantity interacting with the boundary of the region. And so the first one, the divergence theorem, our sense of derivative is divergence in usually 3 dimensions, and we're relating that to the vector field surface integral around the boundary of some 3-dimensional region W. And then Green's theorem, we're taking in R2 the scalar curl of our 2-dimensional vector field integrated across a region in the plane D, and comparing that to the line integral along the boundary curve with set orientation, that we choose the boundary curve that goes around so that the region interior is always to the left as a convention. And so these 2 theorems can help either way. Often it's, if you're interested in the circulation or the flux, these quantities on the boundary, it will sometimes be easier to take the derivative and do the integral over the bulk. Sometimes it can be the case that if you want to do the bulk integral of some scalar quantity, you will look to see if you can find a vector field that is compatible with it, that whose divergence is your scalar quantity or whose curl is your scalar quantity, and then do the corresponding thing on the boundary, which I've mostly seen it for, it's possible to write a vector field with constant curl 1, and then you can compute area by going around the boundary, and it's kind of cool. But the problems that we have, that I've produced here to talk about, are going the sort of potentially more usual direction, where we've got information about this vector field, and we're trying to compute something about its behavior on the boundary by converting to the bulk. And so here we've got this vector field, we've got a cylinder lying above the unit circle, and we want to compute the flux of this vector field through the boundary of that cylinder. So through the upper and lower end caps, as well as the sort of lateral surface. And so for all of these things, how they're dotting with the vector field. And so we could do what we had been doing and parameterize these 3 regions, the lateral surface, the upper plate, and the lower plate, produce the appropriate normals pointing, out of the cylinder. But that means that we're going to wind up with, we would have to do 3 pieces of this computation, and working with all these vector quantities could be rather annoying. But we've got something that would be a very nice region to integrate over in cylindrical coordinates, being, exactly a cylinder. And so we might want to take this vector field, compute its divergence, and then do our computation by integrating the divergence over the interior of the cylinder. And so if we look at what is this divergence, the x component doesn't depend on x. the y component doesn't depend on y, and the z component does depend on z. The derivative of cosine 2 pi z is going to be minus 2 pi sine of 2 pi z. And so our divergence is this negative quantity. Well, this quantity with a negative sign in front of it. Right? And so then the integral around the surface of f dot ds that we're interested in is by the divergence theorem is going to be exactly the triple integral. Let me give myself more space for bounds here. The triple integral of that divergence, 2 pi, gonna get the space, 2 pi sine of 2 pi z. And then here in cylindrical coordinates, we're going to need a factor of r, and let's do the theta integral, or sorry, not 2. The theta integral, the r integral, and the z integral. So it was over the unit circle, cylinder height 1. We don't depend on theta, so the theta integral is going to give us another factor of 2 pi. The dependence on r is linear, and so r is going to anti-differentiate to r squared over 2. And then evaluating that at height 1 is going to give us a factor of 1/2. And so we had 2 factors of 2 pi and 1 factor of 1/2, so that's going to leave us with minus 2 pi squared. And sine of 2 pi z dz. The antiderivative of minus sine is cosine, and we pick up a factor of 1 over 2 pi. And so this will give us just 1 factor of pi, and then looking at cosine of 2 pi z, z ranging from 0 to 1. And again, this results in cosine of 2 pi minus cosine of 0, and so this vanishes as well as the other thing that we were doing earlier. Yeah. And, as usual, there's like, does 0 make sense as an answer? And if we think about what this vector field looks like, well, I'm not sure how helpful that's going to be. The vector field, the xy component is perpendicular to the lateral surface of the cylinder, and so it's not contributing anything to the flux along the lateral component, and the positive z component of the vector field, or the z component of the vector field, which is both positive and negative at different points, is orthogonal to the normal vector of the cylinder, which is pointing directly out along the xy plane. And so all along the lateral surface of the cylinder, the vector field isn't contributing anything. F dot ds is 0. And then on the two end caps, so we're thinking, like these upper and lower disks, our normal vector is going to be either just the vector 0, 0, 1, or for the lower disk 0, 0, negative 1. And so it's going to be like purely in the z direction, so the x and y components don't change anything. And our cosine of 2 pi z, because we're looking at height 0 and height 1, is going to be cosine of 2 pi and cosine of 0, which are both 1. So our vector field is, this drawing is very cluttered, but our vector field is pointing upwards in both of those cases with the same magnitude. The same magnitude in the z direction. The same z component would be a better way of saying that. While on the upper plate, the vector field's going to be parallel to it, and the lower plate vector field is going to be anti-parallel, going exactly opposite. And so the two plates are going to cancel each other out. But we would get values for them that we would have to compute if we were doing. Well, if we didn't make that argument and we're doing it sort of by hand. Okay, and then the last problem that I want to talk about is for Green's theorem. And so here we've got a situation in the plane. We've got this, unit square that goes out to 1 and 1, and we're trying to compute the circulation of this vector field, dotted with the tangent element of the curve. But here our vector field is disastrously horrible. It's the antiderivative of that term multiplied against whatever would be necessary for going up one of the sides of this square or something would be just incredibly difficult. But if we look at this vector field, all the complicated things are occurring. The complicated stuff in the y component depends only on y, the complicated stuff in the x component depends only on x. And so we're in this situation where we can talk about the curl much easier than we can talk about the actual value of the thing. And our region is something reasonable to integrate around. This square will actually also make it simpler the same way that the last one did, where we've got only one thing, a square to integrate over, rather than the 4 separate continuous or C1 pieces of the boundary. Cool. And so here, if we want to look at the curl of f, we're going to look at the x derivative of y, and so the derivative of sine is cosine, so we're going to get pi cosine pi x. We're going to subtract off the y derivative of the x component. The derivative of cosine is minus sine, and we get another factor of pi here, so pi sine pi x should be equal sign. So rather than dotting this very complicated vector field against these tangent elements, our integral of f dot ds little s is our integral just over this unit square of pi cosine pi x plus pi sine pi x. Let's put in appropriate parentheses, dy dx. I should have known that I would not leave myself enough space. Right? And this is like a very, you return at long last to like somewhat pleasant integrals. What we get is, for this, we can pull out a factor of pi. Cosine of pi x integrated in y from 0 to 1 is just going to stay as cosine pi x. And then sine of pi y is going to antidifferentiate to minus cosine, and we're going to get a factor of 1 over pi. And then cosine pi y go to 0 and 1 is going to give us -1 minus -1, so that's going to give us -2, and so we get cosine pi x is 2 over pi dx. Integrating cosine is going to, its antiderivative is sine. We're going to pick up another factor of 1 over pi. And then evaluating sine at 0 and sine of pi x at 0 and 1 is going to be evaluating sine at 0 and pi, and sine of 0 and sine of pi are both 0. So the cosine term vanishes, the constant term just gets multiplied by the width of the interval, which is 1, and so we wind up with 2 as our final answer. Which is a lot more progress than we would have made with the original problem as thought of as circulation. Alright, that's the last problem that I had prepared. So this will be the end of section, and next week is the week of the final.